recording. One, A, B, and C, they are all going to come out the same, but for the sake of being thorough, what is the derivative of each one of those? All right, they're all 4x minus 3. What we're going to do today, though, are antiderivatives, and here's the thing. When you go backwards, are they necessarily all the same function? Well, no. What is different about them? The constant is different. You could add 1, you could add negative a million, okay? You could actually add nothing. The constant could be 0. You don't know. So when you go backwards, you have to put a plus c. So your antiderivative is an inverse of a derivative, and you need to remember to put plus c. So I teach this by basically just thinking backwards, and I kind of just throw everybody in, and I'm like, here, let's just think about it. You need to come up with a function that if you did the derivative, the answer would be 0. It's like you were given the answer, you want to come up with the question. So what's a function that would have a derivative of 0? 3, negative 5, 12, 17. In other words, c, a constant, and we just call it c. Okay? Let you guys do that. All right. Now you need to come up with a function that if you did the derivative, you would get negative 3. Negative 3 is the answer. I want the question. Good. Negative 3x plus c. Sweet. How about just 5? Nice. All right. Now I'm going to throw a variable in there. Okay. When it is x, you need to come up with a function that if you did the derivative, you would just get x. X would be the answer. Is 1/2 x squared. I'm going to pause and let it kind of sink in. If you did a power rule, the 2's would divide out. You would subtract 1. So we're just going to do it backwards. And if you want to write yourself a note, you can. Your notes belong to you. You add 1 to the power and divide by that number. So you add 1 and divide. For a derivative, you multiply and subtract, but they're inverses, kind of like socks and shoes. You know how you put on your socks and then you put on your shoes? When you reverse the process, you take off your shoes and then you take off your socks. Are you following me here at all? Like, you're reversing the process. Now, I'm not done with that one. 1/2 x squared plus 10x plus c, divide. You're going to add 1 to the power and then divide, because for a power rule, you multiply. When you do it backwards, you're going to divide. Sorry, my handwriting is very good for math symbols, but then when I go to write actual words, it's horrible. So sorry about that. All right. Divide is what that says, though. All right, x to the third. You're going to add 1 to the power and divide by that. So what do you think? Yep. 1/4 x to the 4th plus c. Now this has a 1/3 in it. What I do is just ignore it. Kind of like, I don't really like that 1/3. I'm just going to ignore it. All right. It would be 1/6 x to the 6th. Okay. 1/6 x to the 6th. Are you with me? But if you multiply 1/6 times 1/3, you get 1/18. Good. So just kind of cover it up for it, then plus c. Cover it up for a second, think your way through it, and then put it back. Or yeah, you do you. As long as you end up with the right answer, we're good. All right, antiderivative for 3x squared. You want 3x squared to be the answer. I want the question. X cubed, good job. Plus, all right, I want 4x to be the answer. What's the question? 2x squared, good. Plus c. Now you need to come up with a function that when you do the derivative, you get sine. Sine is the answer. Good. Negative cosine, and then plus c. The derivative of cosine is negative sine, but you would need the negatives to cancel out in order for it to be positive sine. All right, for this one, you need a trig function. Now listen to me. There are only 6 trig functions, and it's not sine or cosine. Okay, so you have a 1 in 4 chance of guessing the right one. Which of those 4 that are left has this as its derivative? And you can write on your paper. Secant. Good. So it's secant of x plus c. Do you remember pst? Did you want me to go over it again? Okay. Shh. Pst. It's positive, and if you cover up the one you have, that gives you the answer. So if you have tangent, your answer is positive secant squared. If you have secant, and can't cover that, then your answer is secant tangent for the derivative. All right, antiderivative of cosecant squared. I'll give you a hint. It is going to be negative cotangent. Good. Plus C. E is my favorite one. It's its own derivative, so it's its own antiderivative. It's just going to be 15e to the x plus c. I like that too. That's my favorite one. All right, how about x to the fourth? That would be 1/5 x to the fifth minus e to the x is itself plus c. Cool. You need to come up with a function. Good. Okay, now listen. It is ln. We put absolute value around it because the domain of ln is only positive numbers. You cannot ln a negative number, and so we put the absolute value there. Now that always goes fine, and then for some reason when I throw something like number 15, everyone loses their mind. I want you to rewrite this, taking the 1/3 out of the integral. You're allowed to remove a coefficient. You are not allowed to remove a variable. Don't ever take an x outside of the integral. That is very, very not allowed. Okay. But if you remove that 1/3, hopefully it'll be a little bit more obvious. It's just going to be 1/3 ln x plus c. So for some reason that says 3 throws everybody off. Just remove the coefficient and then you'll be good. That feels like that went okay. Self-assessment, or are we okay? Or do we need a check-in? All right. I told you it was going to go quick. I know this room has been warm this week, so I'm with you on that. All right, fundamental theorem of calculus. It's kind of important. If a function is continuous on your closed interval a to b, I hate when they do this. Capital F is the antiderivative. Like there aren't any other letters of the alphabet. We couldn't have used something other than lowercase f and capital F. Anyway, your integral from a to b of lowercase f of x dx. And do you remember what we did 2 days ago? Or is that like totally, is it evaporated? Do you remember Riemann sums and we were adding up all the rectangles and the trapezoids and things like that? Okay. And then we said if we have an infinite number of them, then that's our definite integral. This is the purpose of the fundamental theorem of calculus is you can find the area under a graph without needing a graph. You don't have to look at it and figure out areas. You can get the answer without a graph is the point of it. You do your antiderivative, which is going to be the capital F, and it is upper boundary minus lower boundary. That should make sense because if you want the area in between two things, you take the bigger one minus the smaller one, and that gives you the area in the middle. Does this make sense? Yeah. Logically? And again, this is why I like integrals so much better than derivatives, is it's very hands-on. It's very visual. It's very tangible. You can like see it and touch it. I feel like there was something else I was going to say about that, and now I forget what it is. So if it comes back to me. I want you to just go ahead and put area. I want you to remember what we're actually finding because that's what it was. People become little correct answer machines and start churning out correct answers just by doing a process, and they have no idea what it is that they're actually finding. Derivative means slope. Integral means area. Those are the two big calculus concepts. I'll say it again. Derivative means slope, rates of change. Integral means area. Those are the two big things. Okay, question. Go ahead. Yeah, good. All right, so we're going to do our antiderivative exactly like we just did on the other side, but we're not going to put plus c. Do you see how this one has boundaries on it? Yeah, okay, that means we're going to actually get a numeric answer. We're finding an area. Did you guys see how the ones on the other side didn't have boundaries? Okay, those are indefinite. These are definite integrals. So x squared, what's our antiderivative? Yeah, 1/3 x cubed, good. And what you're going to do, and please listen, because you guys are at a level where your notation needs to be correct. It's going to get marked wrong if your notation is not correct. Once you do the antiderivative, you no longer put the integral symbol or the dx. It's kind of like this. If I have square root of 36, what's my answer? Do I keep the square root over it? No, I did that already. So I'll get people that'll do this and then keep the integral symbol in there. You did that already. So don't write that. Don't write the dx. Instead, what you're going to do is put such that. It is a such that bar. That's what that means. Such that 0 to 1. Ms. Cole, do I have to put that? Yeah. And then, oh, I feel like we're doing that a lot. Such that. Please, please, please do what I'm going to tell you here. Don't be like, nah, I'm not going to do that. You want to do upper boundary minus lower boundary. Draw blank parentheses. Set it up blank and then just go and fill it in. If you're like, nah, I'm not going to do that, then you're going to have a mistake somewhere. When the problem gets complicated enough, it's about I'm getting on my soapbox here. The majority of mathematics is not about intelligence. It is about organization. I know people that are brilliant and cannot get through a problem because there's just numbers everywhere. Okay, you have to stay organized. So upper boundary, if we plug in 1, what are we going to get? 1/3. There we go. And if we plug in 0, 0. So the answer is 1/3. If you look back at your notes from last time, that's the problem that we did. All those areas that we did, that was it. Okay. All right. Antiderivative of 4x. 2x squared such that 0 to 1. And then you want to do upper boundary minus lower boundary. Set it up blank. Okay. Plug in your upper boundary. That would give you what? 2. Lower 1, 0. So 2. That means the area under that graph is 2. If you were to draw it, but we just didn't have to draw it. Okay. Might not do every single one of these. We're again getting into a place where I think you could probably do that antiderivative. Let's do this one because it's going to involve a negative. I am going to simply rewrite the problem for a second. So I'm going to keep my integral and I'm going to keep my dx. I'm not going to do the problem yet. I'm going to rewrite it. How would I rewrite this? 2x to the negative 2 plus x. Okay. I don't think we had this conversation yet. That's not going to be an ln. ln is only 1 over x. If it's 1 over x squared or 1 over x to the 3rd or 1 over x to the 5th, that is not ln. You have to write it with a negative exponent. Okay. So we're going to add 1 to the power. Careful because it's going to make it less negative. Go ahead.
If it's like 2 over x?
If it's just an x. So if you have 2 over x, that would be 2 ln. Yeah. Good question. All right, so we're going to add 1 to the power. That's going to make it x to the negative 1. And then I would need a negative out front. But it's going to be a negative 2 because there's just a 2 there. The 2 is kind of just there. All right. Plus, and then what's your antiderivative for x? Yeah, 1/2 x squared. Such that, you're not going to put a c, such that 1 to 4. We're going to do upper boundary minus lower boundary. So let's plug in 4. How could you think of this in your mind? Instead of negative 2x to the negative 1, how could we think of that? Yeah, negative 2 over x. Let me just rewrite it that way so that we can see it. So it's a little bit more visual for us. We can think of it like that. So if you plug in 4, you're going to get, what is that? Negative 1/2 plus, what do you think? If you plug in 4 to this part. 8, good. And then if you plug in your lower boundary, if you plug in 1, you're going to get negative 2 plus 1/2, whatever that shakes out to. I believe you could probably figure that out. Okay. Well, I think I'm not going to teach you arithmetic. I'm here to teach you calculus. All right, for this one, do you see that 4 in the denominator? I would remove that from the integral first. And notice I'm not doing the problem, I'm rewriting it. So what's still in there is going to be x plus, and then I don't want to write that as square root. I want to write it as x to the what? What's our power? 1/2. Okay. Okay. So this 1/4 is going to just sit out front. I know it's Friday, but we need to focus better. All right. That 1/4 is going to kind of just hang out front. What did you put for x? We've done this a few times. 1/2 x squared plus. Okay. You need to add 1 to the power. You're not going to write 1 and 1/2. That's not a thing. It would be 3/2. Now, if you want to divide by that, out front, you would put 2/3. You would put the reciprocal. Hold on. Let's let it sink in for a second. if you were to do the derivative, what would happen to these? If you tried to do a power rule, they would cancel. You would just get 1. And then when you subtract 1 to do your power rule, you would get a half. Do you see how we just did it in reverse? Like, let it sink in, okay? Such that 1 to 4. So when you go to do upper minus lower, the 1/4 is just there. I don't have a better explanation than he's just there, okay? And then I would set it up blank. We're going to do upper minus lower like this. Set it up blank.
Oh, so we are more.
Yes. So, and I was actually going to get to that. This is personal preference. I don't like writing the 1/4 2 times because I'm lazy. So I just leave it out front and kind of bracket it off. You could also do 1/4 times and plug 4 in, and then minus 1/4 times and then plug 1 in. That comes down to you do you. It's whatever you want at that point. All right, so if we plug in 4, that's going to be 8 plus, and here's what I'm going to do for this. 2/3 times 4 to the 3/2. You could actually do that because what is the square root of 4? 2, and then 2 cubed is 8, and then you could keep going through that, but again, I'm like, it's kind of like, what are we doing here? All right, and then if you plug in 1, you're going to get a half plus 2/3. I can't imagine a situation where you'd have to get the whole way through that, so we're going to just leave it. Remember, in free response, you're allowed to just stop. I think you'd be okay with this one. Doesn't this look like an easier one? I think we'd be okay with that. All right, let's do this one because it involves unit circle. I'll give you a hint. It's going to be negative. I need a trig function. There's only 6, and it's not sine or cosine. It's one of the other 4 that if I did the derivative, I would get this. Cosecant. Good job. You guys know those. For all the complaining you do, you really know them. All right, such that pi over 4 to pi over 2. Again, what are we finding? What does our numeric answer represent? Area. Because this is what happens. People get good at working them out and have no idea what it is they're actually finding. It is an area. It's an accumulation of area, if you want to think of it that way. All right, so we're going to do upper boundary minus lower boundary. And I'm going to draw a picture for you. If you can just imagine it in your head, that's cool. Where is, and I'm looking for a word like up, down, left, right. Where is pi over 2? Up. Good. That's 0, 1. Cosecant is the reciprocal of sine. Yeah? Or do you believe me? No. Cosecant is the reciprocal of sine. Which value is sine? The y value, which is 1. If you reciprocate 1, you just get 1. Okay? But it's going to be negative. So negative 1. Pi over 4 would be in the first quadrant, and both sides of your triangle are square root of 2 over 2. Now, if you reciprocate square root of 2 over 2, it's going to end up just being square root of 2. You're going to have 2's that cancel out. It's going to be a whole big mess. But if you flip square root of 2 over 2, it's just going to be square root of 2. But it's going to be negative. Here, I'll show you if you want. It's going to look like this. And then when you rationalize, it's going to look like that. And then the 2's divide out. Yeah, so I usually just tell people it's just going to be square root of 2. Okay? I think you would be okay on that one too. You know what? We'll just do the setup for that one. We won't work it the whole way out. Just so you can see visually what it looks like. So we're going to draw our graph e to the x. It's going to be a swoop. Oh, okay, to get into your computer. So there's our e to the x. It's a swoop. We have x equals 0, which will be right here. X equals 2, which would be right here. And y equals 0, which is just your x-axis. So we're finding that area. Hey, thanks. So we're just going to practice setting up the problem. It would be integral from where to where, do you think? Yeah, 0 to 2 of the function e to the x, and then dx is very important. Do you remember what the dx represents? It was only 2 days ago. It is the base of your rectangles. How do you find the area of a rectangle? Base times height. The function is the height. Dx is the base. So it is half of your area formula. Then you can work that out. We'll do this one, and then I'll give you a little brain break before we do average value. Average value is the last thing I need to show you. This one, we do not have an antiderivative for an absolute value. So instead, we're going to draw a picture. Okay? So it's picture time. I would start by plugging in the boundaries. All right, so let's plug in -3. I'll talk you through it. 3 times -3. -9 plus 4 is -5, but if you absolutely value that, 5. Okay, so -3, 5. That went good. You all stayed with me. We found that point. -3, 5. What's our other one? 0. Cool. I like 0. If you plug in 0, you're going to get 4. Perfect. Then you want to find the point of the absolute value. You know, an absolute value is a V shape, right? Or you need to find the point of that. That's going to be where this equals 0. So if you work that out, what are you going to get? -4/3, which is -1 1/3. This is kind of like fun with fractions here. Be like right about there is the point of this V shape. So the area that we are finding is these two triangles, like little kitty cat ears. So how do you find the area of a triangle? All right, good. I'm going to set it up blank. 1/2 base times height for this triangle, and then plus 1/2 base times height for this triangle. We have 2 triangles. Bless you. Now, again, the fractions are where this is going to be tricky. I'm actually going to do this triangle first because I think it'll be a little bit easier. What is the base of this triangle? 4/3. Do you see that there? 1 1/3. The base of that one is 4/3. And what's the height of that one? 4. Good. Okay, that went well. Good job. This one's a little tougher. The height is 5. Okay, we can see that. What do you think the base of this one is? It's 1 and how many thirds? Well, 3/3 would be 1. 2/3. It's 1 and 2/3. Okay, but we don't do mixed fractions. That would be 5/3. Good job. So we're going to look at average value. So the way I remember this is, if I gave you a list of numbers and I asked you to average them, what would you do? Add them all up, divide by like however much you've got, okay? So the integral, and leave a little gap there, I did that on purpose. The integral is what adds up all of your area. You want to think of it as an accumulation of rectangles. You are accumulating area under a curve. Okay, so that's like adding up your list. Oh, I'm sorry, let me move that up. Out front, we're going to put a fraction. We want to divide by however much space we've got in our interval. And the way you can get that is by subtracting. So it's 1 over b minus a. That gives you the length of your interval, and so you're dividing by that. Does that all make sense? It's average. Okay, now the thing people mix it up with a lot is average rate of change. So just real quick, average rate of change, which you did one in the bell ringer, means what? Slope. Yeah, y2 minus y1 over x2 minus x1. Average rate of change is slope. Average value involves an integral. Yes, it is the change or delta x of your subinterval, your interval. What's that? Yes. If that's how it sits best in your mind. Okay, we're going to just set these up. I think if we set them up, you'd be okay to finish them. We worked plenty of them out on the other side of the paper, but let's just practice setting it up. All right, so out front for this one, you would have 1 over 3 minus 1. Hey, Ms. Cole, I know that 3 minus 1 is 2, and I want to just write 2. Be wary of that. Sometimes 0 slips in there, and then things can get a little weird. Also, I like it when my boundaries on the integral match these two numbers. Then I know I did it right. Do you get what I'm saying? It's not that hard to write 3 minus 1, so just do it. You're going to be sad if you subtract something wrong, all right? And then inside of there, you're going to put your, function and then dx at the end. So maybe I'll do like the next step of this one, but I think you'd be okay to finish it. In the next step, I am going to simplify it down. It's a half. And then what's our antiderivative? 1/3 x cubed, good, plus 2x squared, good, such that 1 to 3. And what copy error. So I would leave that 1/2 out front, and then you're going to do upper minus lower. You would just plug in the 3 and then plug in the 1. Just stay organized. It's more about being organized than anything else. We're just going to set up the other ones. I think as long as you got them set up, you'd be okay to finish it. Okay. So what would be our fraction that goes out front for this one? It would be 1 over pi over 2 minus 0. And again, I can't force you to write the minus 0. It's, up to you. But I like it when my boundaries match. Like I can look at that and go, oh, they match. I know I did it right. Right? And then cosine x dx. What would be the antiderivative of cosine? Just throwing it out there. Would it be negative sign or would it just be sine? It would just be sine because the derivative of sine is cosine. So it would just be sine of x. All right, for this one, your fraction out front would be 1 over 4 minus 1. Because see, the common mistake is sometimes people put 1 over 4, and it's not going to be that. It's going to end up being 1 over 3. Okay, so just write it, all right? Integral 1 to 4, 1 over 2x dx. We'll just talk through this one. What is that antiderivative going to end up being? It's ln. You would take this 1/2 and put it out front. Do you see what I'm saying? Here, I'll write it for you. This would be 1/3. You would bring out the 1/2. It would look like this. And then you can see how it's going to end up being ln in the next step. And then you would do upper minus lower. Okay. I'm going to skip this one. I have one exactly like it on the other side. Again, I always just put way more on here than we need. Just if you want to work through that one and be like, hey, did I get this right? I'll check it for you. It's just more practice. But I have one just like this on the other side, so we'll do that one instead because I like the other one better. Oh, I forgot about the properties. We're going to look at our properties real quick. I'm going to use abbreviated notation here. Is that okay with everybody? Just don't tell College Board, okay? Integral from a to a. Technically, I should write f of x dx inside of every single one of these. I'm just not going to do it. Right? What do you think your integral from a to a, how much area did you accumulate if you didn't go anywhere? Yeah, precisely nothing. If you integrate from 1 to 1, you don't have a delta x. You didn't go anywhere. So you've accumulated precisely nothing. Okay. Integral from a to b is the opposite of, or you're negating the integral b to a. It's kind of like you go from home to school, and then you go from school to home, it's backwards. I always think of it like a road trip. And you get that each one of these should say f of x dx inside of it. Yeah. It just gets cumbersome, so I'm not writing it. All right. And then the last one, integral from a to b plus the integral from b to c would give you, what do you suppose? From A to C. And again, I explained that like a road trip. You're traveling from A to C, but you did a rest stop at B. Okay, they're all very logical and they make sense. I'm not going to spend oodles of time over them. We'll just do a couple right here. You're given all this information. From 1 to 4 for x squared is 21. From 1 to 4 of x is 7.5. Now this one does throw people off. So if you want to rewrite it as from 1 to 4 of just 1 dx, sometimes that helps people. What does your graph of y equals 1 look like? Horizontal line at 1, because people are like, shouldn't it just be 0? No, if I draw a horizontal line at 1, there's area underneath of it, isn't there? Like, because people think it'll be nothing. It's not going to be nothing. Okay, so just making sure everybody gets that. So what do you think about this one? Instead of from 1 to 4, it's from 4 to 1, and you just have to find the one that has an x squared in it. What do you think? Yeah. Do you see how this is 21? We just went backwards, so negative 21. You just went the other way. Now this one I threw some coefficients in. It's not any harder. All right, you're going to have 2 and then times, what do you think? What was your integral from 1 to 4 for the x squared? From 1 to 4 is just 21. Yeah, we didn't go backwards or anything. We just times it by 2. Minus 5 times, yeah, the 7.5, and then plus 4 times, not nothing, 3. Okay, that's the one that gets people, isn't it? Nothing. No, there is area under that graph. Okay. And then we'll do this last one using our properties here. You have to be able to find the areas of shapes. Not anything super weird, like you're not going to find the area of a pentagram or something, but or pentagon. But triangles, semicircles, yeah, I meant to say pentagon. Pentagram is like a witchcraft.
That would be really.
Yeah, isn't that a star? I didn't mean to say that. I misspoke. I'm sorry. The lesson. All right. So, but normal shapes like squares, rectangles, triangles, semicircles, stuff like that. All right. So, what is our area for a triangle? Let's find the area of this guy right here. 1/2 base times height. All right. Here we go. What is the base of that one? What is that? 5. 5, and then the height is 4. So what does that shake out to? 10. Good. I'm going to just write that in there. A whole circle is pi r squared. So a semicircle is 1/2 pi r squared. One time on the AP exam, they threw in a quarter circle, which would be what? 1/4 pi r squared. Usually it says it in the directions. Okay. So what is the radius of that semicircle? 3. So 3 squared is 9 and then halves. So it would be 9 pi over 2 or 9/2 pi, but it's actually negative 9/2 pi. Why? Below sea level. It is an unaccumulation. It is like money out of the bank. You're in the red. Does that make sense? Like you're below. Okay. And then you've got this last little triangle. Again, 1/2 base times height. Base is 1, height is 2. So how much is that worth? 1. All right, you're just going to use those numbers to answer all the questions. Here we go. Integral from -5 to 0. What do you think? 10. Good job. From -5, or no, sorry, I was looking at the wrong one. From 0 to 6. Yep, negative 9/2 pi. From 6 to 7, 1. Oh my God. From -5 to 7. So that's the whole thing. You want to add all this together. 11. Yeah, minus whatever that is, Ooh, what do you think about this one? You're going to treat it all like it is positive. Good, because the absolute value. So it's going to be 11 plus 9/2 pi. And then this one, I made it go backwards. You're going from 0 to -5. So you're going from here to here. So -10. Again, it's like driving to school and then driving back home. You're going the opposite direction.